Hello students, welcome to Interconnecting Physics. Today in this video I will teach you about electrostatics, in which we will discuss electric charges and fields. So without wasting time, let's get started. For further updates you can follow me on given links. So in class 12 we have 15 chapters. And today we will discuss about first chapter, that is electric charges and fields. Since chapter is very lengthy, so it's not possible to cover this whole chapter in this video. So we will cover today the sum of the topics of this chapter. The rest of the topics we will cover in upcoming videos. Now let's get started. We start from electrostatics. Electrostatics word is made up of two words, that is electro and statics. Electro means electrical phenomena. Electro means electrical phenomena. And static means at rest. Means it deals with the study of electric force, electric field, electric potential, electric energy due to charges at rest. Means in this topic we will discuss the study of electrons, study of electrical phenomena, study of force, field, potential. The charges will be at rest. So it is called electrostatics. In daily life we see so many phenomena, like during thundering, lightning, during winters when we take off our woolen cloths, we hear crackling sound, some tick tick sound. That is also example of electrostatics. Or when we sit in automobile and after sliding from the seat, when we touch metallic door, we feel a mild shock. Or after walking on woolen carpet, when we touch some metallic object, we also feel a minor shock. These all are the examples of electrostatics. And these effects are due to generation of static electricity, that is electric charges at rest. Now let's discuss electric charge. So electric charge is the physical property of the matter. It is the physical property of the matter. It is also the basic property of electrons, protons and subatomic particles. Even on electric charge I have made a separate video. You can click on I button and watch that video. Electrons are negatively charged and protons are positively charged. There are two types of charges, that is positive and negative. Means suppose we have two charges Q1 and Q2. If both are positive, they will repel each other. If both are negative, they will also repel each other. But if Q1 is positive and Q2 is negative, then they will attract each other. So it means the same charges repel each other and unlike charges means different charges attract each other. And the plus and minus sign which is given to the charge, plus Q1 and minus Q2, these plus and minus charges given to the charge to differentiate two charges is called as polarity of the charge. Charge is a scalar quantity. SI unit of charge is coulomb and denoted by capital C. Now there are so many examples which show there are two types of charges. Like suppose we have a glass rod and a silk cloth. When we rub these two together, what will happen? The glass rod starts losing electrons and silk cloth in turn starts gaining electrons. So glass rod becomes positive and silk cloth becomes negative. So positive and negative. So we have only two options. One is positive, one is negative. So it means there are two types of charges, positive and negative. Similarly, ebonite rod when rubbed with fur, it becomes negatively charged because it starts gaining electrons from fur, and fur in turn becomes positively charged because fur starts losing electron to ebonite rod. So let's discuss now methods of charging an object. So there are three methods to charge an object: charging by friction, charging by conduction and charging by induction. Let us discuss one by one. So first of all we will discuss charging by friction. Friction means rubbing one material with another and it results in losing of electron from one object to another. One of the rubbed object loses electron becomes positive, and other object which gains electrons becomes negatively charged. I have already discussed this example, glass rod and silk cloth. It starts losing electron, becomes positive, and silk cloth starts gaining electron and becomes negative. And the electricity produced due to this method, due to friction method, is called as frictional electricity. And please note that friction is useful for charging insulators. When we have to charge the insulator, we use the method charging by friction. Let us discuss further the charging by conduction. It means charging by physical contact. In this method, we will touch two bodies together. Let's see how. Suppose we have two objects. One is charged, negatively charged, and one is neutral objects. One is negative and one is neutral. One is neutral. Now, we have to charge this neutral body. So, what we do, we touch these bodies together. These bodies are touched together and the electrons from negatively charged body starts moving toward uncharged body. And what will happen after some time when the uncharged body is separated? We see the uncharged body has gained negative electrons and the charged body, which has already lot of electrons, now has less electrons because the electrons are already moved to uncharged body, and uncharged body now becomes negatively charged. Here two bodies are number one touched together and number two same type of charges has been developed. If we want uncharged body to be positive, what we will do, we will take positively charged body and these two bodies then touch together, and what will happen, the uncharged body, the electrons from uncharged body starts moving toward the positively charged body, and after some time when these two bodies are separated, we will see the uncharged body becomes positively charged and this body has less positive charge now because electrons from the uncharged body move toward this body and this body becomes less positive. Uncharged body becomes positive. So we will see same type of charge has been developed here. So now third is charging by induction. This is the final method to charge an object. In this method, two objects are not touched but they are close to each other. So please note, these two bodies are not touched, just they are close to each other. So we will see, suppose we have a positively charged body and a neutral body. Neutral means uncharged body. So what will happen when these two bodies are close to each other, we will see the positively charged body attract the negative electrons from the neutral body and push away the positive charge toward the other side of the objects. So after some time we ground this object. So ground means earthing. And here there are lot of electrons. There are lot of electrons means sea of electrons. Sea of electrons. So what will happen? The positive charge which has been developed here now move toward this sea of electrons. And after some time when these two bodies move apart, we will see the negative charge has been developed on the uncharged body. So in this method we see one, the two bodies are not touched and opposite type of charge has been developed. You see, opposite charge has been developed. So these two methods, charging by induction and charging by conduction, these are helpful for charging conductors. Now these were three methods. Now we will discuss difference between conductors and insulators. Since conductors are the materials which allow the flow of electric charges to pass through them, means charges can easily pass through conductors. But insulators, in which charges are not allowed to pass through them, is called insulators. Now in conductors there are large number of free electrons and these electrons are free to move about in the whole conductor. In insulators there are no free electrons. Now due to presence of free electrons, the charge can be easily spread over the conductor. How? since we have already discussed in charging by induction and charging by conduction. So even when some charge is given to the conductor, it immediately spreads over the whole surface of the conductor. Suppose object becomes positively charged, so positive charge will spread over whole of the conductor, and similarly negative charge will spread over whole of the conductor. But in insulators, the charge remain fixed at one position because these charges cannot move, and the special point is charging by rubbing here is used to charge the insulators. Now there are some examples: silver, copper, aluminium, iron, mercury, earth, etc. And examples of insulators are glass, rubber, plastic, paraffin wax, PVC, etc. Now the basic properties of electric charge. There are four basic properties of electric charge. Number one, additive nature of electric charge, conservation of electric charge, quantization of electric charge, invariance of electric charge. So let us discuss one by one. So additive nature of electric charges. Since additive means to sum up. Additive means to sum up. And since charge is a scalar quantity, it means simple algebra can used to add the charges. We don't need here vector algebra because charge is a scalar quantity. So let us say we have one body, charged body, and we have 3 points A, B and C. Let us say Q1 charge is present at point A, Q2 charge is present at point B and Q3 charge is present at point C. So total charge on the body will be sum of these charges, that is Q1 plus Q2 plus Q3. And if we see at point C, if there is charge minus Q3, then total charge will be Q equal to Q1 plus Q2 plus minus Q3. So here we took the example. We have 4 charges, 1 microcoulomb, 4 microcoulomb. Sorry, we have 3 charges, 1 microcoulomb, 4 microcoulomb, 6 microcoulomb. And the total charge will be 1 microcoulomb, 4 microcoulomb, 6 microcoulomb equal to 11 microcoulomb. So number 2, conservation of electric charge. It states that total charge of the isolated system is always conserved. Conserved means constant. So let us discuss this by taking some example. Suppose we have a body and suppose it has 2 points and charge is 2 microcoulomb and 3 microcoulomb. So total charge will be 5 microcoulomb. Let us shake this body. Let us shake this body. So we will see the charge on the body is now 4 microcoulomb and 1 microcoulomb. Means total charge will be constant before shaking, after shaking. Total charge 5 microcoulomb. Now charge has been distributed and the total charge here is also 5 microcoulomb. So means before the process and after the process charge is same. So it is called total charge of the system is always conserved. So let us discuss more deeply. Suppose we have a body which has charge 3 microcoulomb, 4 microcoulomb and 1 microcoulomb. So let us shake this body. Now you see total charge on this body is 4 plus 3 7 plus 8 microcoulomb. Let us shake this body, and after shaking let us say here 5 microcoulomb and Q. Now you have to find the Q. You have to find this is the application of conservation of electric charge. Now you have to find the Q. Now we know according to conservation of charge, total charge before shaking and after shaking should be equal. So we write 8 microcoulomb, which is total charge before shaking, which is equal to total charge after shaking. So 5 microcoulomb plus Q. 5 microcoulomb plus Q. Now let us solve this. 8 microcoulomb minus 5 microcoulomb. The result will be 8 minus 5, 3 microcoulomb. So in this way, by using conservation of electric charge, we can also solve some numericals. Okay, and here is another example, that is when we rub two objects. One object gains the charge and the other object loses charge. But before rubbing and after rubbing, the total charge of an isolated system is 0. We have already discussed this example, charging an object by friction, in which we took glass rod with silk cloth. So next you see quantization of electric charge. It states that charge on an object, that is Q, is equal to integral multiple of n multiple of basic charge. We write basic charge as E, and we write integer with n, and total charge on the body is Q. See, n can be positive, n can be negative. N can be negative integer, n can be 0, n can be positive integer. And the basic elementary charge has value 1.6 into 10 raised to power minus 19 coulomb. So suppose we have n equal to minus 2. So Q will be put the value of n, that is minus 2, and put the value of E, that is 1.6 into 10 raised to power minus 19 coulomb. And this will be minus 3.2 into 10 raised to power minus 19 coulomb. So in this way we can calculate the total charge on the body. Then the fourth property is invariance of electric charge. Invariance means not changing. Invariance means not changing. So it states that the value of charge on an object does not vary with the speed of the object. Means object is at rest or object is in motion. That does not affect the value of electric charge. It means the charge of an object is independent of the speed of the object. That is, charge at rest is equal to charge in motion. So these were the four properties of electric charge. Now let us discuss the difference between electric charge and mass. Electric charge is derived physical quantity and mass is a fundamental quantity. It plays an important role in electricity, and the mass plays an important role in gravitation. Charge may be positive, may be negative. Mass of body is always positive. Charge is quantized. We just discussed Q equal to NE, that is quantization of electric charge. So charge is always quantized. Mass of body cannot be quantized. Charge of an isolated system is always conserved, but mass is not conserved. According to Einstein mass-energy relationship, energy can be converted into mass and mass can be converted into mass. Mass can be converted into energy. So we can say that mass is not conserved. Charge is invariant. Here the fourth property, invariance of electric charge, that is charge at rest equal to charge in motion. But the mass of body changes with the speed of the body according to the relation m equal to m naught divided by 1 minus v square upon c square. Till now you just learn this, and in upcoming videos I will tell you about this relation, and we will discuss how the mass of body changes with the speed of the body. Number 7. The force between two charges may be attractive or repulsive depending upon the types of charge. And the force between masses is always attractive because gravitation force is always attractive. Now, the Coulomb's force, the most important, the Coulomb's law. According to this law, the magnitude of force of attraction or repulsion between any two objects at rest, because we are discussing electrostatics, so two charges at rest, is directly proportional to the magnitude of the charges and inversely proportional to the square of the distance between them. So, let's discuss. Suppose we have charges 2, Q1 and Q2. If both are positive, they will repel each other, these arrows, and both are negative, they will also repel each other. But if one is positive and another is negative, they will attract each other. So that's why Coulomb's law states that magnitude of force of attraction or repulsion is directly proportional to product of the magnitude of the charges, that is Q1 into Q2, and number 2, inversely proportional to the square of the distance. See, square of the distance between the two charges. Now combining these two equations, we will get F is directly proportional to Q1 Q2 over R square. Or when we remove this proportionality sign, we will get a constant of proportionality, small k, which is called electrostatic force constant or Coulomb's constant. And this Coulomb's constant depends upon number 1, the system of unit used, and number 2, the nature of medium in which charges are placed. The system of units used means force, charges and distance are measured in SI or CGS. This will affect the electrostatic force constant. And the nature of medium means charges are placed in vacuum, in air or in medium. This will all affect the Coulomb's constant. Since Coulomb's constant depends upon the system of unit use, so let us discuss Coulomb's law in SI and in CGS system. So Coulomb's law in SI. Since we write Coulomb law as F equal to small k Q1 Q2 over R square. Now K depends upon SI units. So let us see. K, the value of K in SI is 1 over 4 pi epsilon. This E. This is called as epsilon, and it is called as absolute permittivity. Now it is the combination of two quantities. Let us open up this 1 over 4 pi epsilon naught epsilon r. This epsilon naught, this naught means free space. This epsilon naught is called absolute permittivity of the free space, that is vacuum or air. And this epsilon r is called as relative permittivity of the medium. Epsilon r is purely a number, it has no unit. But epsilon naught has the value 8.85 into 10 raised to power minus 12, and the units are Coulomb square, Newton inverse square. I will tell you how to calculate the units. Now, so F can be written as, put the value of K here, 1 over 4 pi epsilon naught epsilon r Q1 Q2 over R square. But if we discuss Coulomb law in free space, that is in vacuum or air, so we can write the epsilon r relative permittivity is equal to 1. Hence this equation can be written as F equal to 1 over 4 pi epsilon naught, since epsilon r is 1, Q1 Q2 over R square. And the value of 1 over 4 pi epsilon naught or small k is equal to 9 into 10 raised to power 9 Newton meter square Coulomb inverse square. So let us calculate the unit of epsilon. Since F equal to 1 over 4 pi epsilon naught Q1 Q2 over R square. So let us cross multiply. Epsilon naught equal to 1 over 4 pi F Q1 Q2 over R square. Now the SI unit of charge is Coulomb. So Coulomb into Coulomb. 4 pi has no unit and force is measured in Newton, and the SI unit of distance is meter, here meter square. So Coulomb square Newton inverse meter inverse square. So these are the units of epsilon naught. Now 1 over 4 pi epsilon naught. Since F equal to 1 over 4 pi epsilon naught Q1 Q2 over R square, let us cross multiply. We will get 1 over 4 pi epsilon naught F into R square divided by Q1 Q2. So F is measured in Newton, distance is in meter, and the SI unit of charge is Coulomb. So Coulomb 2 times square. So the units will be Newton meter square Coulomb inverse square. And you know K is equal to 1 over 4 pi epsilon naught. So K or 1 over 4 pi epsilon naught both has the same value, that is Newton meter square Coulomb inverse square. And remember students, never cram the units or dimension formula. Always learn the formula, and if you know the formula, then you can calculate any unit of any physical quantity. So let us discuss further Coulomb's law in CGS system. Since the small k has value 1 over capital K in CGS, where capital K is dielectric constant of the medium. Hence Coulomb's law can be written as Fm equal to 1 over K Q1 Q2 over R square. For air or vacuum, K is equal to 1. Means for free space, we take K equal to 1. So we write Fa, that is A means air. The force between two charges when two charges are placed in air. So if K is 1 for free space, so we can write Fa equal to Q1 Q2 over R square. So this was all about the Coulomb's law in SI and CGS. Now let us discuss further characteristics of Coulomb's law. Number 1, electrostatic force between two charges may be attractive or repulsive. Hope you understand. If two charges are of same sign, they will repel each other. If two charges are of opposite sign, they will attract each other. And electrostatic force between two charges obeys inverse square law, because in formula F equal to 1 over 4 pi epsilon naught Q1 Q2 over R square. So that's why it obeys inverse square law. The electrostatic force between two charges is a central force. Central force means, suppose we have two charges Q1 and Q2. So the force which exerts between these two charges, it will always along the center of the line joining the two charges, means center of the line joining the two charges. If Q1 is exerting force on Q2, then the line joining is along from Q1 to Q2. And if Q2 is exerting force on Q1, then the force will act along the line joining from Q to Q1. So means it is a center force. It acts along a line joining the centers of two charged particles. Number 4, electrostatic force between two charges is a conservative force. Electrostatic force between two charges is spherically symmetric because it is a function of R, because it is depending upon R. Electrostatic force between two charges is two-body interaction. Suppose we have three charges Q1, Q2 and Q3. So let us say we are calculating the force between Q1 and Q2. So when we are calculating the force between Q1 and Q2, then the presence of Q3 will not affect the force between Q1 and Q2. And if we are calculating the force between Q1 and Q3, then the presence of Q2 will not affect the force between Q1 and Q3. So means it is two-body interaction. It is not affected by the presence of other charged particles. So number 7, electrostatic force obeys superposition principle. I am going to tell you what is superposition principle. First we discuss limitations of Coulomb's law. Number 1, Coulomb's law is valid only if the electric charges are at rest. If charges will be in motion, then Coulomb's law will not be valid. Number 2, electric charges must be point charges, means the distance between two charges Q1 and Q2 should be very large as compared to the size of the two charges. Then two charges are said to be point charges. Number 3, the separation between two point charges must be greater than nuclear size. You know, nuclear size is 10 raised to power minus 15 meter. So the distance between two charges must be greater than 10 raised to power minus 15 meter. If it is not so, then nuclear force dominates over the electrostatic force. And we want to calculate electrostatic force, but electrostatic force is not coming because the size is less than or equal to 10 raised to power minus 15 meter. So which force will come? That is nuclear force will come. So if we want to calculate the electrostatic force, if we want to discuss the Coulomb's force, then the distance between two charges should be greater than 10 raised to power minus 15 meter. And number 4, it is not universal law. So now let us discuss Coulomb's law in vector form. Suppose we have, now first of all, you should know why we are going to discuss Coulomb's law in vector form. Because in magnitude form, we have already discussed 1 over 4 pi epsilon naught Q1 Q2 over R square. So then what is the need of Coulomb's law in vector form? Because the force is a vector quantity. It has both magnitude as well as direction. So now in this expression, in this equation, we have only discussed about magnitude of the force. But the direction of force is not visible here. So we have to discuss the Coulomb's law in vector form in order to find both magnitude and direction of the force between the two charges. So let us consider we have two charges Q1 and Q2. The distance between two charges is small r. Let us say F12 vector is the force on Q1 charge due to Q2. So F12 is the force on Q1 charge due to Q2, which is equal to 1 over 4 pi epsilon naught Q1 Q2 over R square, and the direction. Now see the direction carefully, since force on Q1 due to Q2 means Q2 is exerting force on Q1. So the direction will be from Q2 to Q1, which is given by R21 unit vector. That is 21 means from 2 charge to 1 charge, from Q2 charge to Q1 charge, and the unit vector is used to specify the direction of any physical quantity. So here we write R21 unit vector. Similarly, F21 vector is the force on Q2 charge due to Q1, which can be written as F21 vector equal to 1 over 4 pi epsilon naught Q1 Q2 over R square, and the direction. Now this time the Q1 is exerting force on Q2. So the direction of force will be from Q1 to Q2, that is given by R12 unit vector. Now we see from the diagram the direction of R21 unit vector and R12 unit vector is opposite. So we can write R21 unit vector is equal to minus R12 unit vector. So substitute the value of R21 unit vector in equation number 1. We see 1 over 4 pi epsilon naught Q1 Q2 over R square brackets minus R12 unit vector. Now take negative sign out from this expression. Expression 1 over 4 pi epsilon naught Q1 Q2 over R square R12 is same as that of equation number 2. So we write here F12 equal to minus of F21. So this is Newton's third law. So we see that Coulomb's law in vector form obeys Newton's third law. Newton's third law. So it means if F12 is action, then F21 is reaction. So Newton's law states that for every action there is equal and opposite reaction. So this was all about Coulomb's law in vector form. Let us discuss Coulomb's law between two charges in terms of their position vectors. Suppose we have coordinate system O, X, Y, Z and we have two charges. Q1 is at point A, Q2 is at point B. R1 vector is the position vector of Q1 from the origin and R2 vector is the position vector of the Q2 from the origin. So we write F21. Force on Q2 charge due to Q1, which is equal to 1 over 4 pi epsilon naught Q1 Q2. Now the distance between two charges is AB. So AB modulus square and direction is, since Q1 is the force on Q2 due to Q1, means Q1 is exerting force on Q2. So the direction will be from 1 to 2, means from A to B. So we write R12 unit vector. So we write here R12 unit vector. So let us find the value of R12 unit vector using triangle law of vector addition. So in triangle OAB, we write OA vector plus AB vector is equal to opposite vector, that is OB vector. Keep AB vector in left hand side and take OA vector in right hand side. Put the value of OB vector and minus OA vector. So OB has value R2 vector and OA vector has value R1 vector. So this is R12. AB vector equal to R12. So AB modulus is equal to R2 minus R1 modulus. Now you see R12. What is the definition of unit vector? The definition of unit vector is vector, given vector divided by the magnitude of vector. Now the vector is AB vector and the magnitude is AB magnitude. So now substitute value of AB vector, which is R2 minus R1, R2 minus R1, and AB modulus is R2 minus R1. Now substitute all these values in this equation. Now AB whole square, AB R2, you see AB whole square, AB is equal to R2 minus R1. You can say AB modulus or you can say AB. So R2 minus R1 whole square, and put the value of R12. R12 is R2 minus R1 vector divided by R2 minus R1 vector magnitude. Now let us multiply R2 minus R1 whole square and R2 minus R1. Since base are same, power can be added. So the equation will be F21 vector equal to 1 over 4 pi epsilon naught Q1 Q2 R2 minus R1 vector divided by R2 minus R1 magnitude whole cube. Similarly, F12 vector is 1 over 4 pi epsilon naught Q1 Q2 R1 minus R2 vector divided by R1 minus R2 whole cube. Now you see, in left hand side it is 2 1 and in right hand side it is also R2 minus R1, means order is same. It is just to remember. So F12 is also the order is same, 1 2 1 minus 2, and we pronounce this equation as F12 1 over 4 pi epsilon naught Q1 Q2 R1 minus R2 vector divided by R1 minus R2 whole cube. Now from equation number 1 and 2, it is clear that F12 is equal to minus F21, means it also obeys Newton's third law of motion. So next, superposition principle. I have already told you the seventh characteristic of Coulomb's force, that is superposition principle. Now let us discuss superposition principle. It is also called as Coulomb's force between multiple charges. So it states that net force on a given charge, means total force on a given point charge due to a number of charges is equal to the vector sum of individual forces acting on that point charge due to all other point charges. Let us discuss. So let us say we have coordinate system O, X, Y, Z. We have n charges Q1, Q2, Q3, Q4 up to so on Qn. Since it's very difficult to show a lot of charges in this page, so for our convenience we have taken only 3 charges, that is Q1, Q2 and Qn. N can be 100, N can be 1000, N can be lakhs, N can be crores, but for our convenience we take only 3 charges, that is Q1, Q2 and Qn. So let us say we have a test charge, that is Q0, on which we have to find the total force due to all these charges. Suppose if Q1 is exerting force on Q0, so we say it as F01 vector. If Q2 is exerting force on Q0, we say it as F02 vector. And if Qn is exerting force on Q0, we say it as F0n vector. We add these forces, see individual forces, and we will get the total force on this test charge. So come to the definition again. It states that the net force acting on a given point charge due to a number of charges around it is the vector sum of individual forces on that point charge due to all other point charges. Why vector sum? Because force is a vector quantity. So we have to use the vector algebra to add the forces. So let us consider we have a number of point charges Q1, Q2 up to so on, and having position vector R1 vector, R2 vector, Rn vector. You see here R is written in bold letter. Bold letter is also means vector. It can be written as like this. But in many books you see the vectors are written in bold letters. So for confusion or for removing your doubts, I have written here R1 in bold so that you can come to know the bold letter or the arrow over some letter is same as that of vector. So let us discuss. We have point charges Q1, Q2, Qn having position vectors Rn vector, R2 vector, Rn vector respectively. Let Q0 is the test charge at point P having position vector R0 vector. Let F01, F02, F0n are the forces on the test charge Q0 due to charge Q1, Q2 and Qn respectively. Then the total force on the charge Q0 can be written as F vector equal to F01 vector plus F02 vector plus up to so on F0n vector. Now substitute the values of F01, F02, F01. So you don't need to calculate the value of F01. You just remember this formula F12 equal to 1 over 4 pi epsilon naught Q1 Q2 R1 minus R2 vector divided by R1 minus R2 whole cube, and use this relation here. So F01, using this relation, F01 vector becomes 1 over 4 pi epsilon naught Q0 Q1 0 R0 vector 1 minus R1 vector divided by R0 minus R1 cube. Similarly, F02, 0 means Q0, 2 means Q2. 1 over 4 pi epsilon naught Q0, Q2, R0 minus R2 divided by R0 minus R2 whole cube. And F01 vector equal to 1 over 4 pi epsilon naught Q0, Qn, R0 minus Rn divided by R0 minus Rn whole cube. So substitute all these values in equation number 1. You will get the total force acting on the test charge Q0 due to all other charges. So relation is 1 over 4 pi epsilon naught q naught q1 r naught minus r1 over r naught minus r1 cube, and similarly so on. So this is the final relation of superposition principle, which tells us about the total force on the test charge q naught due to all other charges around it. If you want to write this relation in the summation form, then we can write as q naught, because q naught is coming in every term, so it can be taken outside. 1 over 4 pi epsilon naught is also coming in every term, so it can be taken outside from the summation. And the summation I starts from 1 to n. This I is the limit of the summation. It starts from 1 to n. So we write q1, q2, qn as qi. R naught is same in every term minus ri. R1, R2, R3, Rn is can be written as Ri divided by R naught minus Ri. Suppose we have I equal to 2. So we can put Q2 R naught minus R2 divided by R naught minus R2 Q. So this was all about superposition principle, and which is used to find the total force on the test charge due to all other charges around it. So this was all about today's lecture. Thank you very much. If you want PDF notes, then you can tell me in comment section, or you can follow me on Telegram. Don't forget to like, share and subscribe. Stay healthy, stay happy.